want to just make this video to kind of answer a question that often shows up, at different points if you're taking a linear circuits course, or if you begin to start taking classes in transistor courses and so forth. It becomes kind of important. And this question basically is, how do I get some of the independent sources like current sources, and how do I get the dependent sources? They show up all over the place, and sometimes, in a linear circuits course, you feel like they're just added sources there to just make your life miserable. Because we want to create more stuff, right? And the answer is no. They exist for a very good reason, is that they show up in most of our nonlinear circuits. They show up in most of our transistor circuits, and we really need to think about how, really think about how to actually use them, and as a result, we often create these voltage-controlled current elements, or we create voltage-controlled voltage sources, or we create other kinds of things because we tend to need them, or we tend to build them, and we need to find a way to approach it. Now, typically that'll require looking at how you linearize various phenomena. And if you're really going to be careful about linearizing phenomena, you need to always make sure that you have some data to support what you're doing, typically, within the regions you're looking at. It is certainly true that any circuit, any nonlinear element is always linear over some small enough region. But it's always important to kind of make sure you have some sort of linear type of dynamic and effect when you're looking at it. And what turns out to be really important, and particularly if we look at this for what is typically a MOSFET transistor, and you could get a similar property with a BJT transistor, is if I take the source voltage at ground, the gate voltage is fixed, although I could put it at different fixed values, and eventually I can make it an input, but let's start with it being fixed. And I'd fix the drain voltage at a high enough, and I take the drain voltage and not fix it, but actually just sort of sweep it in different voltages and then measure the current. I could ask, what kind of curves do I see? Well, and here would be such a set of measurements where, you would imagine saying, I get something that sort of starts off here at a sort of goes up from 0, comes up to a particular potential, and then becomes fixed. This is for a MOSFET operating in subthreshold operation. What I get for one gate voltage, what I get for a second gate voltage and third gate voltage. And one of the things you notice is that it's relatively constant in the way, at least in the view that we're seeing it here. And in fact, for this one, it almost looks really flat, and you're thinking, wow, what kind of source do I know that looks roughly, that doesn't change with current, right? So the current is roughly constant with voltage, and you're like, well, that's a current source. And you're like, wait, current sources are real, and that's a real way to build them. And your answer is yes. This is precisely one of the concepts that shows up, is that transistors are fundamentally current source type of elements. And that turns out to be really interesting, that you basically are looking at current source elements. And also then by changing the gate voltage, I'm changing the current source. And you think to yourself, well, wait a minute. That means for a fixed gate voltage for a transistor, it acts like a current source. Now I could make it better or improve it, and there's all sorts of conversations to be had there. But fundamentally, it's a current source. And you're like, oh, that's pretty cool. And in fact, now if I have I use my gate voltage as an input, what am I doing? I'm actually changing the value of my current source. Oh, wait, over some range, that's going to be linear. That's going to give me a result that looks like this. In fact, there's usually a term, GM, which is called transconductance, because you have a conductance, but it's related to a voltage here and a conductance somewhere else. Ah, okay. So that's why you typically will need such elements. And again, it's true for the linear part of the operation that you're going to expect to see something like this. Now, in practice, transistors aren't perfect, and you would end up finding there's some slope to these things, and we can talk about the slopes and their various relations. And one way that people might model a single transistor to ground is that you might have a resistor in parallel with it, because at least at one level of looking at the data, it kind of looks constant. So that kind of works. Okay. And so now I get multiple linear elements. This is, of course, a nice Norton equivalent circuit for this. And I can proceed. And you think to yourself, wow, there's a reason we're doing these circuits. And particularly if you're in a linear circuits class, you go, why would we keep asking those questions? And the answer is, it shows up everywhere. And so as you start to think about transistor circuits, it shows up everywhere. Now, you can talk about similar sort of things in voltage amplifiers, and if you've done linear circuit classes, you've probably seen an op-amp. You might even see an op-amp with resistive feedback, and so it makes sense if you have an element like this. I can also do circuits where, which might be, say, two transistors, like a common source amplifier, or a source follower amplifier. An op-amp, of course, is actually made out of transistors. In fact, an op-amp can be really, its definition is kind of fluid depending on how you design this and what the numbers you get, and it often depends on the technology, the things you're working with. All right. The other two that tend to be interesting is like current to voltage. So you basically say I'm taking a current from somewhere and outputting a voltage, right? So this is your current control voltage sources. This is typically seen in transimpedance amplifiers because you typically use this in instrumentation all the time, where you say I have an input current, I want an output voltage. In fact, you can actually think about it in the simplest implementation using an op-amp, saying I have an input current and I have some resistance in the feedback. That does give me voltage to current. There's a couple other ways to do that. And although I don't want to spend a lot of time on this, you can also talk about current amplifiers where you go current control current sources, which are typically like a Norton amplifier. There's things that are sort of base circuits that you get for like a winner-take-all circuits that tend to be current in and current out that give you the same idea. But what happens is that all these things are buildable, and all these things are very much physical circuits, and we start by teaching these abstractions in linear circuit classes because fundamentally you're going to need them elsewhere. And they're really tied to physical things, but in many cases in a linear circuits class, the point is not saying what is the physics initially, but how do you begin to think about all these pieces and how do they come together? And that kind of just even allows you to go deeper into what is the physics and what is the concepts that I might need to be solving.